Hi everyone, I'm Nikhil, and today I'll be presenting our work on proportional aggregation of preferences for sequential decision making. This work would not have been possible without my amazing collaborators Shashwat, Goel, and Dominik Peters. These days, AI is being increasingly used to make decisions, for example, recommendations, hiring, and more. Specifically, consider a system which makes decisions repeatedly for a group, say over multiple rounds. The simplest way to make these decisions is to take the alternative in each round, which has the highest support. In such a case, however, a majority may dictate all the decisions, leading to an unrepresentative outcome. Thus, we would like a system which provides durable guarantee on fairness to all the participants to incentivize social cohesion of the collective. We study this problem from a social choice theory-based formalization. More specifically, let n be the size of the group and t be the number of rounds, where in each round, the set of alternatives may be different. In the online version, the alternatives may even be unknown a priori, and even the time horizon t may also be unknown. Next, let each voter approve some subset of the alternatives in each of the t rounds. In every round, one alternative is to be chosen as the decision. Voters who approve that alternative receive one utility. Finally, you would like to report a decision sequence t of length t as the output, and let UID be the total utility received by voter I from t. This basically represents the number of rounds approved by voter I in this decision sequence. This problem is when studied from the online setting is known as perpetual voting, and from the offline setting is known as multi-issue decision making. Now that we have formalized our problem setup, let's see how we can formalize fairness from the ideas of proportionality. We say that a group agrees in the round if there is an alternative in that round which is approved by all of them. Based on this, we can now state the central idea behind all of our proportionality axioms, which is the following: that any group of alpha percentage of the voters which agrees in beta fraction of the round must approve at least beta times alpha percentage of the decision. So suppose there's a 50, we are 50% of the whole population and we agree in all of the rounds, then what this states is that at least 50% of all the decisions should be approved by us. Or alternatively, suppose we are 50% of the voters and we agree in only 50% of the rounds, then at least 25%, which is basically 0.5 times 0.5, 25% of the decision should be approved by us. More concretely, let S be a group which constitutes alpha fraction of the voters. We say that S is happy in a round if at least one member of S approves that round's decision. Based on this, we can now introduce the first proportionality axiom, which we call proportional justified representation, or in short, PJR. It says that if S agrees in every round, so essentially beta is all the rounds, which is equal to T, then it requires the group to be happy in at least alpha times T rounds. Basically, in at least alpha T rounds, one member of S should approve those rounds decision, although this number can differ across rounds. So it is not necessary that a single member should approve all of the L rounds decision. Note that PGR requires S to agree in all of the rounds, which is quite stringent. We can make this more robust by allowing S to agree in some of the rounds. We call this new and more robust axiom strong PGR, and it states that if S agrees in only K of the T rounds, so beta is equal to K, then it requires them to be happy in at least L equal to alpha times beta, which is alpha times K rounds. Now that we have the definitions of the axiom, let's see an example to illustrate the. Consider the following instance where we have 8 rounds and 4 voters. And for every 2 rounds, we have the approval set of the voters. So voter 1 approves alternative A and alternative B in the first 2 rounds, and not any other alternative. Actually, voter 1 approves A and B throughout all the rounds, and voter 2 approves A and C throughout all the rounds. And similarly for voter 3 and 4, but they differ in the last 2 rounds, where voter 3 approves E and voter 4 approves F. Now notice that voter 1 and 2 form a coalition in the sense that they agree on the alternative A across all the rounds. So S is half of the population, like 2 by 4. So alpha is 0.5, and beta, the number of rounds in which they agree, is 8. So what PGR requires is that in at least 0.5 times 4, which is equal to 4 rounds, the outcome needs to be A, B, or C, the alternatives approved by them. Similarly, notice that voter 3 and 4 approve alternative D in the first 6 rounds. So they agree in the first 6 rounds. Thus, beta dash is 6, and they also form half of the population. So alpha dash is 0.5. Thus, strong PGR, which requires the voters to agree in not every round, but is also applicable to some rounds, requires the decision to be at least D, E, or F in 3 rounds so that S dash is satisfied. The question is whether or how we can satisfy these axioms. In fact, in 2021, Batlu et al. Had conjectured that no polynomial time rule achieves PGR. However, we found that the picture is actually much more positive. In fact, in our paper, we show that fragment, a rule which works online and is polynomial time, satisfies not just PGR, but also strong PGR. In the interest of time, I won't be able to go into the proof or how the method works, but this makes us wonder whether we can satisfy even stronger axioms. Now notice that a weakness of PGR and strong PGR is that they can be satisfied even when giving each member of S a utility that is much lower than L. For example, reconsider our running instance where we had 4 voters and 8 rounds, and the correlation S equal to 1, 2, for which PGR required them to be happy in at least 4 rounds. And consider this decision sequence. Notice that here, voter 1 is satisfied from the first 2 rounds since it approves B, and voter 2 is satisfied from the third and fourth round as they approve C. Thus, overall, the correlation S satisfies PGR through this decision sequence. But notice that the individual utility of each voter is 2, which is much lower than 4. This can be fixed from an alternative decision sequence where in the first 4 rounds, voter 3 and 4 are happy, and in the last 4 rounds, voter 1 and 2 are happy, each getting individual a utility of 4. Now let us formalize this notion of guaranteeing a voter at least L utility. We will call this axiom extended justified representation. More specifically, strong EJR says that suppose a correlation S agrees in K of the T rounds, so beta equal to K, then it requires that at least one member of S should approve at least L equal to alpha K rounds. More concisely, there should exist a voter I in S whose total utility should be bigger than or equal to L. This establishes a hierarchy of the axioms. Here, an arrow implies an implication. So strong EGR implies EGR rating beta equal to T, and it also implies strong PGR because if we have at least one voter I whose total utility is at least L, then as a whole, the correlation is also happy with L rounds. Now, actually, you found that fragment does not satisfy EGR, which makes us wonder whether there's any other rule which can satisfy EGR. However, we show in the paper that finding an online rule satisfying EGR would resolve a major open problem in multi-winner voting. This seems to present an obstacle, but can we evade this difficulty with some foresight? Indeed, there is a rule called the method of equal shares, or MES in short. This rule is used in practice for participatory budgeting and can be adapted to our setting in a semi-online manner. That is, it needs to know the time horizon, but can be operated online otherwise. I'll briefly describe the rule. Now, each decision similar to Falvin costs 1 unit, which is paid by supporters. Since we know there are T rounds, the total amount of money required would be T units. And what MES does is divide this pool of money uniformly among the voters to give each voter an equal budget of T by N units. Now, in each round, for each alternative, MES divides this cost as evenly as possible among its supporters and chooses the one which offers the highest bang per buck. Or equivalently, it chooses the lowest maximal cost alternative which are affordable by its supporters. We show that MES satisfies EGR, but it fails strong PGR. The reason for that is suppose there is a large cohesive group, then MES satisfies them repeatedly in early rounds until their money exhausts and then moves on to the other groups. Then if there's another smaller group which only agrees in the initial few rounds and disagrees later totally, then it might be too late by the time MES reaches to them. We have been unable to find a semi-online rule satisfying both EGR and strong PGR, so we leave it as an open problem for future work. Now it seems even more difficult to satisfy strong EGR in semi-online format. So it makes us wonder whether it is possible to satisfy strong EGR in offline settings, where alternatives and approval sets from all the rounds would be known in advance, example of which is multi-option referendums in practice. Indeed, we show in the paper that there is a rule called PAV which satisfies strong EGR. It computes a decision sequence T, which maximizes the sum of the harmonic progression defined by each voter's utility. One might go even one step ahead and ask whether further strengthenings of strong EGR are possible to satisfy. Unfortunately, we show that further strengthening may not be satisfiable in general, as in asking slightly more than alpha times beta may not be satisfiable in general. This completes our discussion on the kind of axioms that we can satisfy, and let's see how our rules can be applied in practice. Suppose you want to automate decision making. For example, one reason could be that preference addition costs are high, so it is not feasible to query a user to obtain its preferences, in which case you might want to learn a machine learning model based on past data of the user. To prototype our application, we use the model machine dataset, a modern take on the trolley problem. It contains millions of pairwise preferences from users around the world on how they would like to act given an ethical situation. Specifically to automate, we learn separate preference models for each country. And on test line, we query the country model to receive its preferences and use a voting rule on top of it to aggregate the responses and get the decision for that round. As the baseline for comparison, we train a single universal model on equal number of responses from all the countries. For evaluation, we use the Gini coefficient, which measures the inequality among the utility distribution of the voters. Specifically, a lower Gini coefficient corresponds to a more equitable utility distribution. As we can see, the combined model here has higher Gini coefficient compared to our aggregation rules. Here, approval voting is a rule which chooses the alternative which has the highest support or approval in every round, so it maximizes efficiency. Across different settings and parameters, what we found consistent is the fact that aggregation using our rule leads to a more equal utility distribution than the combined model. To conclude, here is a table summarizing our key theoretical results for across different settings. Further, the main takeaway from our experiments is that training a combined model on even balanced data may not guarantee fairness because correlations may exist, and the underlying model by nature optimizes for predictive accuracy, which is inherently majoritarian. This completes our presentation, and here are the references. Thank you for your time.